In this problem, a force of 1,000 newtons is required to stretch a spring 0.020 meters from its equilibrium length. So here's a spring that is at equilibrium. It's just at rest sitting there. And then we apply a force of 1,000 newtons, and that causes this delta x. The spring got longer by this much, and that's 0.020 meters. And it's stretched to the right, so delta x is a vector, and to the right is our positive direction, so that's a positive value. This force is in the positive direction. That's the external force required to get it to move. Now, something that's a little bit tricky here is that the spring force, which I'll write down here, Hooke's law says that the spring force is equal to minus k delta x, or sometimes it's written as F equals minus kx. So either way, x is how much the spring is compressed or stretched. Okay, x or delta x. Either way, that's meaning the same thing. But there's this minus sign here in Hooke's law, and that's because we're talking about the spring force, and the spring force is in the opposite direction. The spring is exerting a force to the left. So for instance, if I grab this with my hand here, that's a really terrible looking hand, but if I were to grab that with my hand, I am pulling to the right, but the spring is pulling to the left on me. And so that's the spring force. The spring force is in the opposite direction of the displacement. So if it ends up getting stretched to the right, the spring is pulling to the left, and vice versa. So this is what we're going to use for, we'll call it part A, for finding the spring constant. Okay, call that part A, and this part B. So let's go ahead and execute part A. So 1,000 newtons, and that is to the left. Okay, so we're filling in the spring force. The spring force is 1,000 newtons to the left, so that's negative 1,000 equals minus k times positive 0.020 meters. So then we can divide both sides by negative 0.020 meters. We have the negative sign there, 0.02 there. Okay, and then we get a k of 5 times 10 to the 4th, or 50,000. And the units are newtons per meter. And that's the units that we should get for spring constant. All right, now for part B, that one, that's where we're asked to find the spring potential energy. So spring potential energy, and this equation is also on your equation sheet and in your textbook, is equal to 1/2 k times delta x squared. So you see, a lot of students, it's easy to get these confused, especially when you're first starting out. But this is for force, and this is for energy. So we take this down here, and we can do part B. Spring potential energy, 1/2 times 5 times 10 to the 4th newtons per meter times 0.020 meters squared. So we're taking this value and putting it in right there. And so then plug these values into our calculator, and we get 10 joules. Let's just take a moment to think about those units. We have newtons per meter for the spring constant, and then we're multiplying by meters squared. So if we have meters squared, that cancels with that, and then we're left with newton meters right there, and that leads us to our unit of joules. So the answer does have the correct units. That makes sense. Energy should be measured in joules, and we do get joules. We didn't just assume that it is. We looked and saw that it is. We did answer both parts. The sign of the answers, are they correct? Oh, we forgot to put that in. All right, so we were trying to find k. K is a spring constant. It is a scalar, so it's always positive, and it should have units of newtons per meter. And then potential energy is always positive, and it has units of joules. So sorry about that. We really should have done that at the beginning. We did get the correct signs. Are the magnitudes reasonable? I think this is a tough one to be able to judge, so we'll just leave that as we're not really sure.